This is the third lecture in the mini course on the exceptional theta correspondence, specifically the PGL2 F4 exceptional theta correspondence. And so last time we talked about lifting principal series representations from PGL2 to F4, and we described the proof, or at least a few aspects of the proof. And then at the end, we were about to get to the discussion of spin 9 distinguished F4 representations. And so that's where I'm going to pick up today. So today, we will try to do three things. So the first is just a brief discussion, some basic definitions about distinguished representations. All right, and then we'll talk about how we can characterize the spin 9 distinguished representations of F4. Okay, and then after that, we'll talk about the spin 9 relatively supercuspidal F4 representations. Free to stop me at any point if you have any questions. All right. And next week, we'll get started on the dual group of a spherical variety. Okay, but for today, let me begin with just let me begin with a discussion of distinguished representations. All right, a little bit of notation to get us started. So today, F is just going to be a p-adic field. G to be the F points. For this initial discussion, G is just going to be the F points of a split connected reductive group. Linear algebraic group. Right here, G, this will be the set of isomorphism classes of irreducible smooth G representation. One of the main local problems in the relative lengths program the main problems in the relative local language program is to investigate, describe the following G representations. Look at smooth functions on, I'm sorry, I should say what H is first. Let me add up here. So if we're given some H, let's say that this is an algebraic subgroup. Like to investigate or describe the G representations, smooth functions on the quotient G mod H. And this can be realized as an induced representation from H to G of the trivial representation of H. And this is the smooth version of the problem, and there's also an L2 version of the problem. I just want to focus on the smooth version. Okay, and this problem is somewhat vague, so let me just, for today, I'll make two very explicit, I'll state two explicit problems. They're related to this main problem. Okay. So for one, we might like to classify those smooth irreducible representations of G that possess an H invariant linear functional. And we know by Frobenius reciprocity that this is equivalent to finding the sub-representations of an induced representation. And then another problem is if we have an H distinguished, oh, sorry, let me also just add, such a representation in part one is called H distinguished. Maybe we don't even really need that representation to be irreducible. Okay. Now let's suppose that pi is H distinguished. And let's choose some non-zero linear functional in this space, some non-zero H invariant linear functional. And some non-zero vector in the space. And then we can look at the generalized matrix coefficient. Of this phi sub v comma lambda of G. This is going to be a function on G, and it's just defined as lambda applied to G inverse acting on V. All right, so this is going to be a smooth function on G mod H. And then we can ask the following question. Is this compactly supported? Let me be maybe a little bit careful here. So let's ask, is this generalized matrix coefficient, is this compactly supported? Modulo the center of G H. Oh, okay, you're asking about this here? Yeah, okay, so if I do it on the left, yes, that's correct. So yeah, thank you. with spin 9 sitting inside of F4, we can use the PGL2 cross F4 theta correspondence to solve these two problems. Let's go down. All right, let me just take a moment. Any questions on the setup? So after this, we'll review some of the setup from the exceptional theta correspondence, and then we'll talk about how we can attack these problems. But any questions on the setup before we go? All right. Let's begin with just a little review from last time, just to reset some notation. So we have pi v. This is a minimal representation of a split adjoint group of type E7. Inside of E7, we have the E6 levy. Sorry, the E6 parabolic. And we'll take a levy decomposition Mn. All right, one of the important features of this parabolic is that if we have this unipotent radical, we could identify this with a cubic Jordan algebra. (27-dimensional Jordan algebra. And O is the split octonions. Okay, if we take this parabolic and we intersect this with our dual pair, this PGL2 cross F4 dual pair, what we'll get is, well, this completely contains the F4 factor, so you have all of F4, but then its intersection with PGL2, this becomes a Borel of PGL2. Borel of PGL2, and let's say that we have a Levy decomposition T times U. This T, this can be identified with the center of the Levy subgroup. And this U, this is sitting inside of N. N we can identify with the cubic Jordan algebra, and this U can be identified with the line generated by the identity elements in the cubic Jordan algebra. Oh, and just for emphasis, let me, I'm using, this is different notation from last week. We also needed an additive character, non-trivial additive character for field F. Then if we have some irreducible representation of let's just say PGL2. Then we had the big theta lift, which came from taking the minimal representation, and we could project onto V sub tau. This is the maximal, sorry, tau, no tau, pi. V sub pi, this is the maximal pi isotypic closure. This maximal tau isotypic, this maximal pi isotypic quotient also has an action of F4, and so this representation can be factored into a tensor product. And then that F4 factor, this is the big theta representation. I'm sorry, the big theta lift of pi. Okay. I think that's all we're going to need for today. Last time we talked about little theta as well. We only need big theta today. Okay. All right. I started with a representation of PGL2, but in fact, we could flip and start with an irreducible representation of F4, and we can do the same type of construction. So I'll also talk about the big theta lift of an F4 representation. And the big theta lift of an F4 representation, that will be a PGL2 representation. All right, in our analysis last week, we had two important tools. We'll see both of them again, but I want to specifically remind you about one. So we had this P minus means opposite, and this P minus filtration of the minimal representation, which looked like this. So we have our minimal representation, and we can project onto the n minus co-invariance. And the kernel of that projection can be modeled on smooth, compactly supported functions on this set omega. And omega is just going to be the rank 1 elements in J. Our Jordan algebra. And this sequence is exact. It's an exact sequence of P minus representations. And as a reminder, this is sort of like a partial Schrodinger model. All right, I want to highlight two facts. I won't prove these two facts, but we'll need them for the main theorems. And then we can get down to proving the characterization of spin 9 distinguished F4 representations. So first, if I take an irreducible representation sigma of F4, then its big theta lift, this is either irreducible or 0. And so then if it's non-zero, then big theta is equal to little theta. So we're not going to see that today. All right. Okay, and then furthermore, if we're in the case where the big theta lift is 0, that is not 0, then in fact, sigma is self-dual. All right, so now let me state the theorem on the spin 9 distinguished representations of F4, and we'll go through at least a sketch of the proof. Again, this is coming from my joint work with Gordon Salmon. All right, so let's let sigma be an irreducible representation of F4. And then we have the following two statements. Let me call this. Okay, so first, the dimension of the space of spin 9 invariant linear functionals is at most 1. And second, we have equality if and only if sigma is the theta lift of a generic PGL2 representation. I'm sorry. Need to just go back and fix 2. Let's see. So we have equality. So that Hom space has dimension exactly equal to 1 if and only if the big theta lift of sigma, which is a representation of PGL2, is generic. All right. Oh, I need to recall one other thing. Okay, so we have F4, and we talked about how this can be identified as the algebra automorphisms of the 27-dimensional exceptional Jordan algebra. And inside this algebra, we can look at the stabilizer of a particular vector. So remember, this 27-dimensional Jordan algebra, this can be realized as 3x3 matrices with particular properties, but one of those matrices is the diagonal matrix 1, 0, 0. And we can look at the stabilizer of this. This is going to be some subgroup of F4. Okay, and this is isomorphic to a group of type spin 9. This is how we're going to realize spin 9 inside of F4. And let's just call this subgroup H. Right, so let's just start with exactly the object that we're looking at. So we want to understand the H invariant linear functionals of sigma. All right, well, the first thing we can do is we can apply Frobenius reciprocity, turn this into an F4 Hom space. The trivial representation is now replaced by the induced representation from H to F4 of the trivial representation. Okay. We can dualize this Hom space. Now we're looking at maps from compactly induced induction from H to F4 of the trivial representation into the smooth dual of sigma. And we can use our facts. Yes, fact 2 from above. So this says that, I guess I should see here. I'll just carry this around for a second. I'll come back to that in a moment. Okay. This is a step that I'll justify a little bit later. Okay, but what's going to happen is we can relate this compact induced representation to the minimal representation for E7. And in fact, this is going to be the Jacquet module of the minimal representation. Specifically, this step is following because the Jacquet module, the PGL2 Jacquet module of the minimal representation of E7 is isomorphic to this compact induction from the spin 9 subgroup to F4. Okay, but for now, let's just assume that. Okay. Okay, now if we have an F4 homomorphism from this Jacquet module to sigma tilde, this is going to have to factor through the sigma tilde maximal isotypic quotient. I'm going to be skipping, I'm going to leave out a few details here. The point is that we can pass to this quotient. So this is going to look like sigma tilde tensor theta sigma tilde. Okay, this theta sigma tilde, this is our PGL2 representation. So the PGL2 co-invariants are attached to that. Use the tensor Ham adjunction to get okay, and then by Schur's lemma, the second factor is just isomorphic to C. And so we get big theta of sigma tilde into C. So I got to write down the co-invariance. Right, in other words, this is just the space of Whittaker functions. Okay, so now the dimension of this space is less than or equal to 1 by the multiplicity 1 theorem for Whittaker models, for Whittaker functionals. And then fact 1. Just as a reminder, fact 1 is just saying that if I take an irreducible representation of F4 and I do its big theta lift, then it is either 0 or irreducible. So now the dimension is equal to 1 if and only if the big theta lift of sigma tilde is generic. Okay. All right, and then finally, by fact 2, this sigma is self-dual. Basically, when this theta is on 0. Okay, so this proves the theorem modulo the claim. So next I'll justify the claim, but any questions on the proof so far? Just as a reminder, what is this? This is that we take the minimal representation and we apply the Jacquet functor. This is isomorphic to compact induction of the trivial representation spin 9 up to F4. So this is as F4 representations. So this is going to use our tool 2 from last time, this P minus filtration. Let's see, but maybe I want to. That's okay. Yeah. So let's consider the P minus filtration. Okay, this is an exact sequence, and we're going to apply the Jacquet functor, the PGL2 Jacquet functor. That's an exact functor, so we get an exact sequence. Minus over there. And now the first important point is that the right-hand term, this is 0. And this is because U minus sits inside of N minus. And so if you first take trivial coinvariance, but then you take twisted coinvariance with respect to a subgroup, that's going to kill everything. Okay, so then in particular, that inclusion is actually an isomorphism. For isomorphism. Separate out a lemma. We need to understand the coinvariance of this space of functions. There's sort of a standard strategies for handling this. Let me just write out what the answer is going to be, give you a reference, and I'll make a few comments about this a little bit later. Okay. So if we take the coinvariance of this function space, okay, this is going to be isomorphic to smooth, compactly supported functions on this set omega sub 1. What is this? These will be elements of omega. And remember that omega sits inside of the Jordan algebra. These will be those elements that have trace equal to 1. I'll sort of explain where this comes from a bit later. So in other words, these are smooth, compactly supported functions on the elements of rank 1 and trace 1. So to prove something like this, you can follow the argument in lemma 2.2 of Magard 7. And this is from a paper in Compositio from 1997. All right. Okay. So now we need to understand this space of smooth compactly supported functions on the rank 1, trace 1 elements of the Jordan algebra. And we can realize this as an induced representation, because in fact, this is a homogeneous space. So this I will also just sort of state as a fact. So F4 acts transitively on omega 1. Omega 1 contains this element that we discussed earlier, diagonal element 1, 0, 0. I'm going to call this X naught. So H was exactly the stabilizer. Stabilizer in F4 of X naught. Both of these facts are discussed in Springer belt count. On exceptional structures. All right, so with this choice of X naught, we get an isomorphism of F4 representations. It's not so hard to write it down explicitly, but I'm going to skip over that. So the smooth, compactly supported functions on omega 1, this can be realized as an induced representation, where we are inducing the trivial representation from, I was calling that H, from spin 9 up to F4. Okay, so if we put everything together, we get the theorem. Just as a reminder, what is the theorem? Is that if we take the PGL2 Jacquet module of the minimal representation, that as an F4 representation is isomorphic to inducing the trivial representation from spin 9 up to F4. Any questions about the proof of that theorem? All right. Okay. Let's say a few more words about why we're seeing trace 1 elements appear. Okay, so for this, we need to recall a little bit more closely the action of the parabolic on the minimal representation. So from last time, let's see, so what do I need specifically? So let's suppose that we have n minus, this is going to be in unipotent radical of the opposite parabolic. And let's take a function in smooth compactly supported function on omega, which is again just the rank 1 elements. So the action of n minus on F comes down to multiplying F by an additive character. So the input is the pairing between n minus and x. So just a quick reminder. It's on the side. Omega is sitting inside of J, a Jordan algebra, and that can be identified with n. Okay. And the n minus, this is sitting inside the opposite parabol. Okay. So this pairing, this is really just coming from the killing form. Killing form on the Lie algebra of E7, but we restrict to, right now we're just restricting to n and to n minus. Okay, but we have the following. So we have this pairing on n and n minus. But we know that n can be identified with JO, and n minus, I was sort of skirted this point. I was not so careful about this earlier. This can be identified more correctly with the dual of the Jordan algebra, but then the dual of the Jordan algebra can be, then the dual of the Jordan algebra can be identified with the Jordan algebra itself using the trace pairing, which is going to be non-degenerate. So under these identifications, between n minus and x, this can be realized as the trace between n minus viewed as an element of the Jordan algebra times x viewed as an element of the Jordan algebra. But now we're interested in sort of the U minus psi coinvariance. And from earlier, this U minus, which is sitting inside of n minus, the n minus can be identified with the Jordan algebra. I think I said this earlier, the U minus, this gets identified with the multiple of the line through the identity element. Okay. So for U minus, which let me write this as C times that identity element, we have the following. U minus paired with X. This is going to be the same as the trace. I'll do it in 2 steps. This is going to be the trace of C times the identity times X. And this is just C times the trace of X. Okay, so let's just go back to what we were interested in. We're looking at these smooth, compactly supported functions on the rank 1 elements. We're taking the U minus psi co-invariance. Okay. We want to identify this as some other space of functions. And we know that U minus times F of X, based on our previous discussion, this is exactly psi of C times the trace of X times F of X. Here, just to say this again, this U minus has been identified with C times the identity in the Jordan algebra. Okay. So really the only time that u minus acts through psi well, this is going to happen when the trace of x is equal to 1. Here, the point being that psi of u minus, this is just going to be psi of c. All right, so this is the reason why we're seeing the trace one elements appear in this co-invariance calculation. There's some more details that need to be checked, but this is the essence of their appearance. So this concludes the first part on the characterization of the spin 9 distinguished representations of F4. Now, any questions on that? Yes, please.
Some kind of wild coverage of the so I'm just following
I think maybe it is not always a vial conjugate, but yeah, it is often a vial conjugate. But sorry, what was your question again?
Yeah, my question is maybe we should build this U minus as some kind of wild conjugation of some U. Then we have a foil transform instead of thinking like the form something.
But even, I mean, when you have a Fourier transform, you need some sort of pairing. I think it will boil down to be the same thing at the end. Yeah. But in fact, you don't, part of the point is that you don't need it to be conjugate at all. I mean, these things are, there is a sort of canonically defined opposite parabolic. And on these structures, we have an identification with the dual Jordan algebra, and then through the trace, we can line it up with the Jordan algebra of the original parabola. And we are sort of, well, let me not say anything. Let me not say anything more. Yeah. They are compatible, and I've been a little. I haven't specifically written down some of these isomorphisms, namely the isomorphism of the unipotent radical with the Jordan algebra. And some care should be taken there for sure. Okay. All right, so let's move on to the final topic for today. I want to discuss the spin 9 relatively supercuspidal F4 representations. Okay, so I'll state the proposition. We'll go through the proof, and then I'll mention a very recent result by two folks from NUS, like a converse to what I'll write down now. So, so in my paper with Gordon 7, this is proposition 8.3. So let's let sigma be an irreducible representation of F4. if sigma is isomorphic to the theta lift of pi. So if sigma is isomorphic to the big theta lift of pi, where pi is an irreducible smooth representation of PGL2, and it's also supercuspidal. Take a supercuspidal representation of PGL2. We look at its theta lift, we get some F4 representation. So if we are in that situation, then sigma is spin 9 relatively supercuspidal. Again, maybe we switch at the scale. A few preliminaries. Okay, so the first is that sigma is H is spin 9. Spin 9 relatively supercuspidal. This will happen if and only if sigma can be embedded in the smooth, compactly supported functions of F4 by spin 9. And this is just this compact induction. And then as we just saw, this compactly induced space, we can realize this in terms of the minimal representation. So this compact induced space, as we just saw, is isomorphic to the minimal representation of E7, where we take the PGL2 twisted covariance. Okay, so in fact, we're going to show that we have such an embedding. Back to the proof. Or rather, restart the proof. Okay, so by assumption, we have that sigma is isomorphic to the big theta lift of some supercuspidal representation of PGL2. We want to get this involved with the minimal representation. And so we also know that the minimal representation surjects onto pi tensor big theta, and this big theta is just sigma. Okay, all right, but now we're going to use something special about supercuspidal representations. Because pi is supercuspidal, the minimal representation, just viewed as a PGL2 representation, this is going to break up. It's going to split into two parts. Different notation, just a little more evocative. Let me tell you what these two subspaces are. Okay, so this first one, and this is just the tau, which the tau again, sorry, all taus are pi. This is the pi isotypic subspace. This other piece is just the canonical complement. And in particular, all subquotients do not contain. All right, and this, okay. So this is a decomposition as a PGL2 representation, but in fact, because F4 and PGL2 commute, this is actually a decomposition of PGL2 cross F4. All right. Let me give this surjection a name. Let me call this. Let me call this map. I'll call this one phi sub tau. So note this phi sub tau, this maps onto the maximal pi isotypic quotient. And so the canonical complement of the pi isotypic subspace, well, this must be contained inside the kernel of phi. So as a consequence of that, the tau isotypic subspace, this is actually enough to get a surjection onto the maximal tau isotypic quotient. All right, but this tensor product, as I just said, is the maximal pi isotypic quotient. Thus, in fact, this surjection is an isomorphism. Skipping a few details, but this is the essence. Okay. All right, so what's the significance of this? So this tensor product is isomorphic to the tau isotypic subspace. I'm sorry. Again, all taus are pi. One of those. Pi, pi, pi. Okay. So the tensor product is isomorphic to the pi isotypic subspace. And of course, this sits inside of the minimal representation, just by definition. All right, ultimately, we need to get back to the space of compactly supported functions on F4 modulo spin 9. But to do this, we just apply the PGL2 Jacquet functor. Once again, this is exact. And so we will get the right-hand side is isomorphic to exactly the induced representation that we want. And on the left-hand side, we get C tensor sigma. This is because the supercuspidal representations are generic. And we have the multiplicity one here. So what we've done is we've realized sigma as a submodule of the induced representation, or equivalently, the smooth, compactly supported functions on F4 mod spin 9. And so it is spin 9 relatively supercuspidal. Any questions on that theory? Okay, and so the final thing I want to do today is I just want to highlight a recent converse. All right, this is due to Nat Hong Lei from NUS here, and Brian Wang, formerly from NUS. All right. Okay, so let's let sigma be an irreducible F4 representation. And let's say that it is not isomorphic to either of two explicit representations, which I'll say something about in a bit. Okay. So we take any irreducible representation of F4, except for possibly two of them, and we get the following. Then sigma is spin 9 relatively supercuspidal. If and only if sigma is the lift, isomorphic to the theta lift of some irreducible supercuspidal representation of PGL2. We just discussed the upward implication. But in fact, the converse is also true, except maybe for these two guys. Okay, so let me just say a final word about what are these two explicit representations. So throughout this mini course, we've been discussing the PGL2 cross F4 dual pair inside of E7. Okay, but there is also a dual pair involving F4 inside of a group of type E6. And in fact, we have mu2, so the plus minus one, group with two elements, cross F4. This sits inside of a group of type E6. Let's take this one to just be split and adjoint. Okay. But in fact, we want to take the disconnected group where the component group is given by the outer automorphisms of E6. So in other words, the diagram automorphism. And in fact, this mu2, this will be this outer automorph. Should just be coming from this diagram automorphism. Okay, now here, the irreducible representations of mu2, this is just a set of size 2. There's the trivial representation, and then there's the sign representation. Okay. And in fact, if we, let's see, we take the theta lift of either of these, let's define this to be big theta plus. Find this one to be big theta minus. Right, both of these are irreducible. Useful representations of F4, and these are the two representations which are excluded in the theorem. All right. Okay. That's all I have to say for today. Any questions? Sorry, say again. Ah. Yeah, so let me just remind you. Yeah, so we didn't really see little theta today, and that was because the lifts that we were dealing with today, the big theta was already irreducible. But the whole point is just that, okay, so from last time, let's say pi is an irreducible representation of PGL2. This little theta, this is defined to be the maximal semi-simple quotient of big theta. So if big theta is irreducible, then it's already semi-simple. And so in fact, big theta will then just be exactly equal to little theta. Does that answer your question? Yeah, okay. Any other questions? All right. Okay, so that will be all for today. We'll start talking about the dual group of spherical varieties next week. All right. Okay, that will be all for this week.